Hello, everybody. Welcome back. I want to go over a few things that we covered at the very end of last period, and that is the effect of the structure of the base on the product distribution in elimination, E2 elimination reactions. So if you see here, we have an elimination reaction. And if you remember, just to review, you have an alpha carbon that contains the leaving group. And then you have beta carbons, right? The ones next door. And this beta carbon has two hydrogens. I'll show one. And this beta carbon has three hydrogens. I'll show one. And so the base can attack this hydrogen. These electrons go in here to form a double bond, and then the leaving group is kicked out. That you see would form this product. And change the color here. The base could, of course, also form a bond to that hydrogen, that beta hydrogen. Then the electrons would come in here to form a double bond. The leaving group gets kicked out. In that case, the double bond forms here, and you form this product. Okay. This product, you see, there's one alkyl group, two alkyl groups, three alkyl groups attached to the double bond. Whereas this one, you have one alkyl group, two alkyl groups. So remember that the alkene with the greater number of alkyl groups attached to the double bond is the more stable one. So this is more stable, and the more stable product is called the Zaitsev product. The less stable product is called the Hofmann product. So you see the product distribution depends on the nature of the base. If you take a small base like a ethoxide, another example of a small base would be methoxide or even hydroxide, they're all small. Then the major product is the more stable alkene, the Zaitsev product. But if you use a sterically hindered base, it's a more crowded base, then you see the major product is the less stable alkene, the Hofmann product. If you use even a more sterically hindered base, we have three ethyl groups now, then you see the less stable product is even more strongly preferred. Okay? So if you're a synthetic organic chemist and want to make one or the other alkene, you can do so by choosing the appropriate base. A small base to form the more stable alkene, a larger base to form the less stable alkene. You see there's a mixture of products in these reactions, and that is called regioselectivity, regioselective. Well, what that means is not that there's a mixture of products, is there a mixture of products and one product is favored. So you get a mixture of constitutional isomers and one product is favored. So it's selective. One of the regions of the molecule is favored for the double bond. Right. So here we're going to do a couple of examples, illustrate this principle. I'll do two examples. So I'll do the second. Okay, we can start with the first one. Here's your alpha carbon. And here's a beta carbon. There's two hydrogens. I'll show one. Here's another beta carbon, but you notice there are no hydrogens on that carbon. There are two methyls. So the only place the double bond can go is there, right? By removing the H and the Cl. And so let's draw the product. Here are your two methyls. Here's the methyl on the carbon with the chlorine, and there's your double bond. Okay. The ethoxide picks up a hydrogen, and chloride is expelled. Leaving group is expelled. Okay. So in the second example, here's your beta hydrogen. You have two hydrogens. I'll show one. You have three hydrogens on this beta carbon. I will show one of them. The double bond, if the base, in this case a small base hydroxide, it could attack this hydrogen. The electrons go there. The leaving group is kicked out. See, that will give you this alkene, 2-methyl, 2-pentene. On the other hand, if the hydroxide abstracts that beta hydrogen, then the double bond forms there. Leaving group is still kicked out. You're going to get the double bond there. Then the major product will be this, 2-methyl, 1-pentene. Okay, which is the major product? Well, this is a 1,2 tri-substituted alkene. This is again 1,2 di-substituted alkene. So this is the Zaitsev. Just to review this. This is the Hofmann. We're using a small base hydroxide, so the more stable Zaitsev is the major product. It's regioselective. You get some of the Hofmann, but the major product is a Zaitsev. In this case, we're using a bulky base, T-butoxide ion, that looks like this. Right? Counter ion is potassium. We have beta hydrogens here. We have beta hydrogens there. It's going to remove that beta hydrogen, the one that's more accessible on the outside of the molecule. That beta hydrogen is more accessible on the outside of the molecule. So the double major product will have the double bond going there. The less stable Hofmann product. Okay. So again, the small bases favor the more stable alkene. The large bases favor the less stable alkene, the Hofmann product. Okay, this slide shows why. Here's a reaction where you can get 2 products, a major and a minor. And here are your reactants in the energy diagram. The 2 products here are a trans product and a cis product. And this is cis, right? This is trans. The trans we talked about is more stable. So these are the products. And here are the this is the transition state leading to the cis product. This is the transition state leading to the trans product. The trans product is more stable. And remember, in the transition state, the hydrogen's being removed, a double bond is forming, and the leaving group is being kicked out. So in the transition state, there's some double bond character. And since the trans double bond is more stable than the cis, the transition state leading to the trans alkene will be lower in energy. And so the activation energy will be smaller and the reaction will be faster.